So first of all, we will look at the concept of translation invariance. In the last lecture, we studied about norm space. So a metric space D induced by a norm on a norm space X satisfies these two conditions. First one states that distance between x plus a and y plus a is same as the distance between x and y. Second is distance between alpha x and alpha y is equal to modulus of alpha multiplied by distance between x and y. Here x, y and this a are elements of norm space X, and alpha is any scalar, means it belongs to a field F. So let us prove these concepts. We know that distance between x plus a and y plus a is equal to norm x plus a minus y plus a by the metric defined on norm, because metric on metric on norm is defined as dxy equal to norm x minus y. So x plus a minus y plus a. So if you open these brackets, a and a will cancel out, so we are left with x minus y. This is nothing but the distance between x and y. Now the distance between alpha x and alpha y is norm of alpha x minus alpha y. We can take alpha common, so outside it will be modulus of alpha, and inside we will have norm of x minus y. The norm of x minus y is distance between x and y. Now the Banach space is complete norm space, means if we define any Cauchy sequence in this space, it will converge to a point in the space. So it is complete in the metric defined by norm. So how we define convergence of a sequence in a norm space? A sequence xn in a norm space X is said to be convergent if X contains an X such that limit n tending to infinity norm of xn minus x is equal to 0, and we call this X as the limit of xn. Now Cauchy sequence. A sequence xn in a norm space X is Cauchy if for every epsilon greater than 0 there is a natural number n such that norm of xm minus xn is less than epsilon for all mn greater than n. Now convergence of infinite series. If xk is a sequence in a norm space X, we can associate with xk the sequence Sn of partial sums, which we write as Sn equal to x1 plus x2 plus dash 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 plus xn, where n is equal to 1, 2, 3 and so on. If Sn is convergent, that is if Sn converges to some point S, and we write that norm of Sn minus S tends to 0, then the infinite series sigma k equal to 1 to infinity xk equal to x1 plus x2 plus dash 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 is said to converge, or we say it is convergent, and S is called the sum of the series, and in this case we write as S equal to x1 plus x2 plus x3 and so on, and in short we write sigma k equal to 1 to infinity xk. Now the sequence is absolutely convergent if norm x1 plus norm x2 plus dash 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 converges the series xk. In that case the series xk is said to be absolutely convergent. In a norm space X, absolute convergence implies convergence if and only if X is complete. The concept of convergence of a series can be used to define bases also. In previous lecture we have studied in detail about bases. So if a norm space X contains a sequence En with the property that for every x belonging to X there is a unique sequence of scalars alpha n such that norm of x minus alpha 1 e1 plus alpha 2 e2 plus dash 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 alpha n en tends to 0 as n tends to infinity, then this en is called a shorter basis or simply a basis for x. And the series alpha 1 e1 plus alpha 2 e2 plus alpha n en, or we can extend as n tends to infinity up to k equal to 1 to infinity alpha k e k, which has the sum x, is then called expansion of x with respect to en, and we write it as x equal to sigma k equal to 1 to infinity alpha k e k. So we have defined the concept of convergence of series. We have defined basis by the concept of convergence of a series, and this sequence in this case is called the shorter basis. In a normed linear space, every convergent sequence is a Cauchy sequence. We are given a sequence which is convergent sequence. Let xn be a convergent sequence in a normed linear space. It means that there exists a limit point x in the space such that limit xn and tend to infinity is equal to x. This is by the definition of convergence. So it means that for every positive value of epsilon, there exists a natural number n in the sequence such that for all n greater than or equal to n, norm xn minus x is less than epsilon upon 2. Since we have control over the term, this norm xn minus 1, xn minus x, we can make the right hand side as small as we want to choose a small epsilon, because here in place of epsilon I have written epsilon by 2. So here we can write any term as per convenience, because we can control these terms. If we consider two arbitrary numbers m and n such that m and n are greater than or equal to n, the norm of xm minus xn is equal to norm of xm minus x plus x minus xn. If we open the brackets, means if we apply the triangle inequality to this, then we can write it as norm of xm minus x plus x minus xn. Because m is greater than or equal to n, so if we replace n by m here, then it will be less than epsilon by 2, and we know that norm of xn minus x is same as norm of x minus xn, so this is also less than epsilon by 2. So epsilon by 2 plus epsilon by 2 means epsilon. Hence the sequence xn, which we have defined like this, which is given to be convergent sequence, satisfies the Cauchy criteria. It means this sequence is a Cauchy sequence. Hence we have proved that in a normed linear space, every convergent sequence is a Cauchy sequence, because we have taken this sequence to be any arbitrary sequence. Now completeness. Every finite dimensional space Y of a normed space X is complete. It means every finite dimensional normed space is complete. Suppose we consider an arbitrary Cauchy sequence ym in Y. Because we want to show that it is complete, we will show that it is convergent to some point y in Y. Because the space is said to be complete if we consider any Cauchy sequence in points of the space and it converges to the point in space. Suppose dimension of Y is equal to n and e1, e2, en be any basis for Y, then each ym has a unique representation of the form ym equal to alpha 1 m e1 plus alpha 2 m e2 and so on up to alpha n m en. Because this ym is a Cauchy sequence, therefore for every epsilon greater than 0, there is a natural number n such that norm of ym minus yr is less than epsilon, where m and r are greater than n. This is by the definition of Cauchy sequence. It means for every c greater than 0, this epsilon is greater than ym minus r, because norm of ym minus r is less than epsilon. So I can write it like this: epsilon greater than ym minus yr. Because ym is equal to alpha 1m e1 plus alpha 2m em, so alpha 2m e2 plus dash dash alpha n m en, we can write it in short as alpha j m ej, where j varies from 1 to n. So here I have written, in place of ym, sigma j equal to 1 to n alpha j m ej. If we apply the same notation and replace m by r, then it will be alpha 1r e1 yr equal to alpha 1r e1 plus alpha 2r e2 alpha nr er, and in short we can write alpha sigma j equal to 1 to n alpha jr ej. So in place of yr, I have substituted the value of sigma j equal to 1 to r alpha jr ej. If we take ej common, we can write sigma j equal to 1 to n alpha jm minus alpha jr, and this is greater than or equal to c times j equal to 1 to n alpha jm ejr. Here m and r are greater than n. Because c is greater than 0, so we can divide it by c. So if we divide it by c, c will come to this side, means epsilon upon c is greater than or equal to this term. Or we can write, if we shift this term to this side and this term to this side, we can write modulus of alpha j m alpha jr is less than or equal to sigma j equal to 1 to n alpha jm alpha jr and less than epsilon by c. I have written in the reverse direction. Here these m and r are greater than n. It means that the sequence, that each of the n sequence alpha jm means alpha j1, alpha j2 and so on, where j varies from 1 to n, is a Cauchy sequence in the set of real number or even in the set of complex number, whatever we have considered. It means it converges. And suppose alpha j is the limit of the sequence. So using these n limits, because j varies from 1 to n, alpha 1, alpha 2, alpha n, we define y equal to alpha 1 e1 plus alpha 2 e2 plus alpha n en. Clearly this y belongs to the subspace y, and we can write norm of ym minus y equal to value of ym is sigma j equal to 1 to n alpha jm and ej, and value of y is alpha j ej, means alpha j ej. In short we can write sigma j equal to 1 to n alpha j ej. So if we take these alphas common, so it will be less than or equal to j equal to 1 to n modulus of alpha jm minus alpha j and norm of ej. So we know that alpha jm converges to alpha j. Alpha jm converges to alpha j. It means ym converges to norm of ym minus y tends to 0, that is ym tends to y. Because alpha jm converges to alpha j, it means this tends to 0 and ym tends to y. It means ym is convergent in y. So we have shown that because in the first line we have considered ym to be a Cauchy sequence, and this is an arbitrary Cauchy sequence in y. It means y is complete, because any arbitrary Cauchy sequence in y converges to a point in y. Here I want to say that every finite dimensional vector subspace Y of a norm space X is closed in X. And in case it is not finite dimensional, then the space need not be closed. Now the equivalent norms. The norm, we can define different norms on any space. So the norms 1, this one have been written to distinguish it from the another norm. So the norms norm 1 and norm 2 defined on a vector space X over a field F are said to be equivalent if there exists a positive constant C1 and C2 such that for every vector X in X, C1 time norm X1 is less than or equal to norm X2 is less than or equal to norm C2 times norm X1. An equivalent norm is a different way to measure the size or magnitude of vector in a vector space. Two norms are considered equivalent if they define the same notion of convergence and continuity on the vector space. And equivalent norms on X define the same topology. So this is very important concept in which we have defined how we say that two norms are equivalent. There is one important theorem that on a finite dimensional vector space X, any norm 1 is equivalent to another norm 2. We are given that X is a finite dimensional vector space over a field F. Suppose dimension of X is equal to n because it is finite dimensional, and here n is any positive integer. Suppose we consider two norms, norm 1 and norm 2. First of all, norm is continuous because in a finite dimensional vector space, all norms are continuous with respect to standard topology induced by the vector space structure. So if we take a sequence xk that converges to X with respect to norm 1, then it also converges to X with respect to norm 2 and vice versa. So if the sequence is convergent in one space, it is also convergent in if sequence converges to one norm, then it also converges with respect to another norm. Now we will show that Y norms are equivalent. Let Y be a subspace of X with dimension Y equal to n. M. Here M is less than or equal to n because Y is a subspace of X. Consider the norms induced by different bases of Y. For any vector X in Y, we can write it as a linear combination of bases vectors, and the norms induced by different bases are equivalent because they produce the same vector coordinates. Now we extend the norms to entire space. Let y1, y2, yn be a basis for Y. We extend this basis to a basis for X by adding n minus m linearly independent vectors, means x1, x2, xn minus m. Now we have the basis for X in which we have these vectors and also these vectors, means y1, y2, ym and x1, x2, xn minus m. So this is the basis for X. So because this is a basis for X, so for any vector X in X, we can write X equal to a1 y1 plus a2 y2 plus am yn plus b1 x1 plus b2 x2 plus bn minus 1 xn minus 1, where a1 a2 am and b1 b2 bn minus 1 are scalars. Because we know that any vector in a basis can be expressed as a linear combination. We define norm x1 equal to modulus of a1 plus modulus of a2 plus modulus of am plus modulus of b1 plus modulus of b2 plus modulus of bn minus 1 as the norm induced by norm 1 on X. Similarly, we define norm x2 as a modulus of a1 plus modulus of a2 plus modulus of am plus 2 times modulus of b1 plus 2 twice modulus of b2 plus dash 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 plus twice modulus of bn minus 1 as the norm induced by norm 2 on X. Now we want to show that these two norms which we have defined like this, norm 1 and norm 2, are equivalent norms. For this we need to show that there exists positive constant C1 and C2 such that C1 times norm x1 is less than or equal to norm x2 is less than or equal to C2 times norm x1 for every vector x in X. This is by the definition of equivalent norms. So if we consider the constant C1 equal to 1 and C2 equal to 2, it is clear that norm x1 is less than or equal to norm x2. As the second term includes additional positive terms. See from the definition. Here this is norm x1, and in norm x2 we have some additional terms, means here we have b1, b2, bn minus 1, here we have twice the terms, 2b1 plus 2b2 plus 2bn minus m. So the second term includes the additional positive terms. So it is clear that norm x1 is less than or equal to norm x2. So to show the reverse inequality, we notice that for any bi in the expression for x2, norm x2, we can write modulus of bi as 1 upon 2 into 2 modulus of bi. We can divide and multiply by 2. So using this, norm of x2 is equal to this is by definition, and this is greater than or equal to modulus of a1 plus modulus of a2 plus modulus of am plus modulus of b1 plus modulus of b2 plus modulus of bn minus 1, and this is norm x1. So we have shown that C1 is equal to 1 and C2 equal to 2 satisfy the condition for equivalence norms. Since this holds for any vector x, we conclude that that both the norms are equivalent on a finite dimensional space. Thank you.